Up next, we have one of our very own, Dr. Kapil Vaswani, who's going to be speaking about the state of confidential computing. Kapil was a security researcher in the confidential computing group at Microsoft Research for 18 years. His research focused on building secure, robust, and transparent systems. He pioneered work on designing secure services, such as databases using confidential computing and new forms of confidential computing hardware on devices like GPUs. Kapil completed his master's and PhD from the Indian Institute of Science in Bangalore, where he worked on performance profiling and modeling techniques. Kapil is currently the head of the SPARC-FRO, a focused research organization here at FSID. Please welcome Dr. Kapil Vaswani.
Thanks for the kind introduction. The talk, my talk today is going to be about confidential computing. But before I get started on the talk, I just wanted to do a very quick poll. How many of you, I mean, this is a very security and privacy focused audience, right? You're all interested in security and privacy. How many of you either directly or indirectly used confidential computing? Okay, I'd say about 20%, right? We'll come back to this question at the end of the talk and see whether you change your opinion or not, right? Okay, so what I'm going to do in this talk is try and give you a sense for this tech that has been in evolution for at least the last 13, 14 years. A journey that I've been closely involved in. But what I'll try and give you a sense for is how it has evolved over the course of the last decade from something that was considered mostly like a toy to a place where it's in very large scale use, and at least some of the sense we have is that it's at the inflection point where we will see over the next few years significant adoption of technology like this to protect security and privacy, a lot of sensitive data that we use on a daily basis, right? So I'll try and give you that sense, and what I'll also try and give you a sense for is where research was involved in some of this, long-term research was involved, and also some of the trade-offs that we've had to make as an industry over the last 10 or 15 years to get to a place where we get adoption at real scale, right? Because it's not been, the vision has changed, the tech has changed over time, and I'll try and give you a sense for what some of those changes have happened and the learnings that we've learned, over the last few years. Okay, so like I asked, right, how many of you use secure confidential computing or secure enclave, right? I don't know how many of you recognize, but this is a chip SoC of an Apple device. Right? This is one of the first uses of secure enclaves or confidential computing. Broadly speaking, since 2013, 2014, Apple introduced in every in iPhones 5S, this secure computing element called as SCP or a secure enclave processor. The basic idea was very simple, right? So you have your main application processor that does all of your computing. But whenever you have to handle anything that is sensitive, like your encryption keys for the disk that is associated with your phone, or for managing encryption keys or backups, things like Touch ID, your passwords and pins and so on, the idea was to delegate it to a separate chip, which is physically distinct from your main application processor. And more than this, the fact that it is physically separate, it's actually designed with strong security in mind, with trade-offs that you would not make for your regular applications, right? So for example, things like following strong security guidelines, writing code in a way that is highly secure, keeping the trusted computing base very small, taking a performance hit wherever required, whenever you want to trade off security. So that was the basic idea, that there is a normal world and a secure world, right? And everything here remains secret. And in fact, I don't know how many of you know the San Bernardino case, right? Where Apple was in fact forced by FBI, or FBI tried to force Apple into jailbreaking a device. At this point, this technology didn't exist in iPhones. This happened with an iPhone 5C. The first time this appeared was in iPhone 5S, right? So just after the San Bernardino case. But the claim that Apple makes today, even till today, is that because of technology like this, they cannot be coerced by anyone to giving access to a device, to someone's device, because they don't have the technical means to go break this kind of an encryption, right? Even if Apple wanted to, and even if it was coerced, they don't have the technical capability, because this device generates its own secrets and protects its own secret, even from the manufacturer and Apple as a service provider, right? So that's the kind of claim that we want to make. And in fact, this now exists in, if you're using Android devices, this small coprocessor on the side, almost pretty much all Android devices today have these security coprocessors. So this is like this idea of having a secure world and a normal world separate exists pretty much everywhere on client side. And the question that we are asking in confidential computing is, how do we do this for all computation, right? How do we design systems where you can isolate an application, any security critical application, and host it in a hardware isolated environment where it remains protected both during transit and in use, but both at rest and in transit, but also in use, right? And remains isolated in a way where only the entity that owns the data has access. Even the entity that's hosting this platform, or anyone else for that matter, the service provider, has no technical way of getting access to that data, right? So that's the kind of claim we want to make. Obviously, there is some trust in hardware, which I'll talk about a bit later, but this is the kind of claim we want to make. So this is something that we hypothesized in, like, back in 2014, is that can we actually run pretty much all workloads in the public cloud this way, where as a cloud provider, you can make a technical case that you have no way of getting access to a tenant's data in the cloud, right? So how do we do this? And ideally, we also want to do this with some kind of verifiability, where it's not just I trust the cloud provider to say that they cannot access data, but it's also that I can verify myself that the cloud provider has no access to this data, right? So that's the remote verifiability part. Now, the first thing we realized that when you want to do this, replicate this kind of a guarantee in the public cloud, one thing that maybe in hindsight is fairly obvious is that these trusted execution environments, they cannot be a separate chip in the cloud, right? We cannot bifurcate the hardware in our cloud to have a normal world and a secure world. That is a non-starter in the beginning. Too much cost, too many operational burdens. It doesn't fly, right? So we cannot take all the big cloud hardware, the big server and big racks, and bifurcate that hardware, including CPUs and GPUs. It's just not tenable in the beginning. So what we realized is that these TEs must in fact be logical environments. They can't be physically distinct, but they must be logical environments that are supported by commodity hardware in the cloud, right? So this was the idea that Intel came out with in 2014 with Intel SGX, software guard extensions, where the idea was that you could take your existing CPU with some trust in this CPU. What you can do is you can create what are called enclaves. So these enclaves are secure processes on a regular CPU. They can be created by a guest operating system, but they are managed fully by the CPU. So the CPU actually manages this entire environment. It manages the state of this process. It encrypts that state when it is in memory, and it isolates that state from everything else on the system, including other virtual machines, including the guest operating itself, and everything below that, the hypervisor, the host operating system. No entity has access into this environment. So this is a combination of memory encryption and isolation. And it gives you two things. It gives you confidentiality, so the state is not visible to anyone else. But more importantly, and this is something we've realized over a very long time, that more than confidentiality, in fact, what's more interesting is integrity. So it gives you this guarantee that you cannot tamper with the state. So you cannot change the flow of execution inside this environment and make this code do things that it is not supposed to do, right? So those are the two guarantees you get, and you get remote verifiability. So if you are a client, so if you are using your device and connecting to a service in the cloud, you can get from the CPU a signed attestation, a cryptographic proof that the entity you are communicating with is in fact running in a genuine piece of hardware, and it's running with the right application. And you can do this verification offline, and then you can release keys into this environment in a way that only this environment has access to. So the cloud has no access to your keys, and you can run your compute, you can give it access to encrypted data, you can decrypt it inside this environment, run your compute, re-encrypt the data, and send it back to the entity that you intended to. So all of this is possible using, in fact, in the manufacturing. So this requires significant effort, and usually not seen. It's hard to see by people who are just using enclaves. Every single CPU that supports SGX is provisioned with a unique device identity during manufacturing. It's fused into the device, And that unique device identity is used to sign these attestations that can then be remotely verified. And Intel, in fact, stands up a service called where you can send all of this attestation and you can get verification that this is still running on a genuine CPU. It's running on with the right kind of firmware, and you can trust this attestation. Okay, so this was 2014, right? So what do we get? What was sort of one anecdote here is that when Intel released this technology, SGX, it did it for desktop CPUs, right? For laptops and desktops, not for the cloud. So that was in 2014, and I still remember playing around with some desktop CPUs in Microsoft, and it was actually not taken very well when we went to Azure and tell them, can you start deploying this technology in the cloud? And they said, these are desktop CPUs. We don't deploy desktop CPUs in the cloud. But actually, we did, right? So at this point, there was enough conviction that this is interesting enough that we could go convince Azure to deploy desktop CPUs in a cloud environment. Obviously, this evolved over time, and there was Coffee Lake and Ice Lake. They were extensions of SGX that supported more memory, that supported more capabilities, and so on and so forth. So this has evolved over 3 generations to get to Intel Ice Lake. In fact, the original version with Ice Lake in 2014 only had, you could only create processes with 128 megabytes of memory in them, right? So this was, and it was due to some very, very strong guarantees that you wanted from enclaves, including the ability to detect if there is a physical attack on memory and if someone is trying to replay cache lines and so on. So it was designed for a very, very strong security guarantees. So this was in 2014, and it led to a whole bunch of research papers, what we like to do in academia, right, on taking existing applications and moving them inside SGX and trying to do this in a way that is efficient and that gives you the right kind of security guarantees, including some of our own work here. So everything from databases to all kinds of system inference, AI inferencing systems and everything. There was sort of a cottage industry trying to move all of these applications to run inside Intel SGX with strong guarantees. But over the course of these 3-4 years, for most part, there was no real big applications that were using this technology, right? Because it was quite difficult to use, and it came with all of these constraints, like the amount of memory available, and so on, and the performance overheads. So the next set of lessons we learned is not just that these must be logical environments in a cloud, but also that if you really want to scale this tech like this, it should not require significant developer effort. It should not introduce a new security boundary. So if you go back to this slide, right, this in the cloud is a new security boundary. In the cloud is designed to give you protection of a virtual machine. It's not designed to give you process of guarantees for protection of a process within a virtual machine. So this was a new security boundary. It introduced high overheads, and if we wanted these to scale, then you should actually reduce these overheads, right? So those are the 3 next set of lessons we learned. And it just so turned out that the solution to these problems did not come from Intel. It came from AMD in the form of this, again, a new kind of trusted execution environments called SEV-SNP, right? And this came somewhere around, I mean, again, this was an evolution, but first supported by Milan processors in 2021. They understood all of these 3 challenges, and the way they solved this is by saying that we are not going to try and isolate process, we are going to isolate virtual machines. Already a security boundary in the cloud, but we are going to do sort of dual protection, right? Virtual machines isolate your workloads from the cloud provider. We are going to try and isolate virtual machines from the cloud provider, right? In the other direction. And they had some other capabilities that essentially give you the same kind of guarantees, but instead of trying to protect a single workload, the goal here is to try and isolate a full virtual machine, including an operating system and all other guest applications running inside it from the rest of the environment, right? Slightly different threat model, but more aligned with how we think about security in the cloud. It did come with some downsides. There was a larger trusted computing base. Now, instead of trusting just an application as a remote verifier, you now have to trust an operating system and all applications inside that VM, right? So definitely larger TCB. And at this point, we also had to give up on this very nuanced property of integrity property of the ability to do replay attacks on memory. If you are interested, come to me and I'll tell you more about what this is, but this is a property that we had to lose because we wanted performance, right? So we lost this, but we gained in terms of mind share. So AMD started evolution of this technology in 2016 but finally landed it in various forms in 2020 in the Milan processors. So it took like a period of 3 generations typically to get to this point. And at that point, it was no longer just Microsoft, but in fact, the Google Cloud also started supporting SNP because they also agreed that this is a more viable solution in the cloud. Right. And then it didn't take time for others to catch up. So in a couple of years from then, Intel switched from SGX to TDX, which is again a virtual machine-based isolation boundary, a trusted execution environment. And at that point, ARM also released something called ARM CCA, which is a specification for how to implement these kinds of trusted execution, VM-based trusted execution environments on ARM CPUs, right? And we gained more clouds. So we had the support in IBM and we had the support in the Alibaba cloud and others. These might not be all fully accurate in terms of time, so all sort of disclaimers here. Okay, so what is TDX? So TDS actually tries to do what AMD SEV tries to do, but in a slightly different way. So again, the idea here is that you have these trust domains, which are essentially virtual machines plus plus, but these trust domains are again protected by hardware, a combination of hardware and firmware that runs in very privileged mode. But essentially, you get the same sort of guarantees, right? That these environments are fully isolated. You can run unmodified applications in them. You need an OS that is slightly enlightened to understand that it's running inside TDX, but that is something that the Linux community has done over time. And this part of the region cannot be seen by these virtual machines, cannot be observed or tampered by the cloud provider, right? So these kinds of guarantees started appearing in TDX, and I won't go into the details, but ARM is essentially proposing something very similar. For those of you know, ARM has always had something called Trust Zone on client devices, but ARM since extended that to support confidential computing in the form of these new domains called realms, right? So the idea here is that these realms are again hardware isolated virtual machines. They have a bit more capabilities, but for most part they are hardware isolated virtual machines that the cloud provider has no access to. The architecture is a bit different, but at a very, very high level, Intel, AMD, and ARM have all converged to this idea of a virtual machine-based trusted execution environment. Okay, so that was these lessons done, but we had to do more, right? So the next step in the evolution was the idea that we must start supporting GPUs. A lot of our workloads run on GPUs. If you don't have support for GPUs inside this environment, you are missing out on a lot of workloads. So this is where we worked very closely with NVIDIA to get these goals, or again, over a period of 4 or 5 years, to end up with confidential computing support inside the Hopper GPUs. So here the idea is that you can in fact create this logical environment, but not just bound to a CPU. You can actually extend that logical environment also to a GPU, which also supports trusted execution. And it does this by supporting a new confidential computing mode. So all Hopper GPUs today support this. There is a new confidential computing mode. In this mode, there is the GPU goes into a state where the host of the GPU no longer has access to the device, right? So the GPU memory, or at least a part of the GPU memory, and all of its security sensitive configuration is fully isolated from the host using PCIe firewalls. And it's only accessible to a trusted execution environment, either AMD or Intel or ARM based, running on the CPU side. So now you can run workloads here. You can set up a secure channel with the device, and you can encrypt and ensure that all state or models or data or queries that you offload from the CPU to the GPU will remain encrypted and remain secured inside the GPU environment. Right? So that's the ability that the Hopper GPU support. And this is now supported in Azure in the form of confidential GPU VMs and also in the Google Cloud in confidential spaces. So that got us to GPUs. The performance actually is already pretty good. It's not where we would like it to be, but it's already pretty good. And in fact, we see this very interesting behavior that the more complex the models, the larger the models you get, the better performance you have, because these trusted execution environments are not compute bound. The overheads of running your code inside these trusted execution environments is no longer bound by compute. It's actually bound by I/O, right? Because you have to encrypt all your data between the CPU and the GPU. And today on the CPU, you can't in fact encrypt as fast as you would like it to. PCIe is like 64 gigabytes a second. You can really mostly encrypt at 4 maybe 5 gigabits a second, right? So the bottleneck is in fact in IO, not on compute. So the larger model you have, in fact, we can go even larger. You can go up to DeepSeek R1, that kind of model, and you see very little performance drop when you run inside confidential computing mode. So this is like in noise, right? So you're no longer paying a cost for running these models in confidential computing mode. Okay, so that changed the ecosystem again. So with NVIDIA again, there are few more, I'm not showing you the whole picture because there were more attempts at doing this even on GPUs before, even in fact with Ampere GPUs, but we finally landed this in Hopper. In the meanwhile, AMD also revved and is supporting these capabilities in Genoa in the latest generation of Genoa CPUs. So that was the next lesson. And the final lesson that we've learned, and there's been a lot of interesting work over the last few years, is to say that not only do we have to support GPUs, but we must support all devices, right? NICs, SSDs, anything that you connect in the cloud must now be allowed inside these environments. And the way you securely assign these devices into these environments must be done using standard protocols and must come with very low overheads, right? If you have overheads of more than low single digit percentages, you are not going to be scaling this technology. So the goal is to do it at low single digit percentage and all devices, right? All devices at least that are willing to adopt confidential computing. So that has resulted in a whole bunch of new work in the industry around a protocol called TDISP. I don't have time to discuss this, but the next generation of Intel CPUs, AMD CPUs, and ARM CPUs, in fact, will have support for TDISP. We don't have this today, but we will get there. And NVIDIA with Blackwell, the Blackwell GPUs is already promising support for TDISP. So when we get to the state, the belief is that we will be able to run very large workloads, including at least get to some scale of, like, for example, large model fine-tuning inside confidential computing environments. Okay, so that was about the hardware, just the hardware, right? But just having the hardware in the cloud doesn't solve the problem. You need developers to build software on these platforms, and you need to help them do this in a way that is secure and gives the right kind of guarantees. Again, I won't have time to discuss the entire picture here, but there are broadly two kinds of platforms in confidential computing. There are VMs that are designed to run legacy applications. So essentially what they call lift and shift, right? To take your existing application and host them inside confidential computing environments. So that's one class of solutions that already exist in the market. And then there are specialized VMs that are designed to run containerized workloads. So if you've containerized your workload, you can actually run them inside these environments with more stronger guarantees, right? And there again, there are a whole bunch of solutions. In Azure, there's confidential container instances, Google Confidential Spaces, Nitro Enclaves, and a newly emerging effort called Kata Confidential Containers, which is designed to be cross-cloud, right? So there is a whole bunch of efforts here on how do you take existing containerized workloads, move them into confidential computing environments, but with strong guarantees, like the ability to attest the entire workload and ensure end-to-end integrity, right? So the idea here is, again, to meet developers where they are instead of asking developers to do more work, or at least do a handshake, right? If you are willing to containerize your workload, then we will meet you where you are and adopt and be able to move your containerized workloads into these environments. And that's what you have to do to get real scale. Again, there are more details on how this works, but in the interest of time, I'll skip this. There is a very interesting idea here of using something called container security policies to ensure that when your Kubernetes cluster brings up a containerized workload, you can remotely verify that it is running exactly the workload that you had the service provider is saying, and that even if the entire Kubernetes cluster and the Kubernetes administrator is compromised, they cannot change the workload that the system is attesting to you remotely, right? And there's more details here. Again, if you are interested, please talk to me offline and I can give you more details. Okay, so I want to go back to this question that I asked earlier. How many of you use confidential computing services, right? So in fact, one of the first adopters of this was Signal. So Signal is, as many of you know, is an encrypted chat application. And it turns out that for some of the tasks that Signal does, I mean, in general, Signal guarantees end-to-end encryption, right? But for some of the tasks, it needs the backend to be able to process data in the clear, right? And they use confidential computing to do this to ensure that they can have backend services that can do processing, but do it in a way where they can continue to give these end-to-end encryption guarantees to their clients. And that has actually now WhatsApp is trying to do this. So if you are using WhatsApp for many of their AI workloads, right, they use confidential computing in the backend to ensure that your data can be processed in the cloud in the backend, but you still get end-to-end protection of your data. Apple recently released something called the private cloud compute. So anytime from your iPhone, you talk to any of the Apple model in the backend, it's running on secure hardware that Apple has created. It's not Intel AMD or ARM, it's Apple's own hardware, but they've created hardwares and clusters to give these kinds of guarantees, and that's called private cloud compute. And there is a lot of interest. So OpenAI, for example, has publicly said that they believe that in the future, the way their infrastructure will be secured, OpenAI and Anthropic, in fact, have said that they will want to secure all of their infrastructure from very advanced attackers, including nation states, using strong technologies, including confidential computing. Right? So there's a lot of interest, but this is where we are not there yet, and there is a bunch of work to do. But that at least is the North Star to be able to protect all of AI infrastructure using confidential computing. There is also very interesting solutions for secure multi-party computation using confidential computing. Azure Clean Rooms and confidential spaces are examples. There are already products that let multiple entities bring data sets together and run analytics and training in ways that ensures end-to-end security. We in India are also pioneering an effort here to a framework that we call DEPA training that allows, again, multiple participants to pool their data sets and train new models. So this is something that is also close to heart because this is something that we in India are also pioneering. So this is still early stage work, but this is something we are pushing. I'll very quickly pause with some challenges and new directions, right? So this might seem all good, but there are lots of interesting both research and in production challenges in scaling this technology. The biggest challenge, perhaps the biggest challenge, is this idea that because we made some of these choices, like we want to have these TEs become logical environments, not physically distinct, that comes with a whole bunch of possible security attacks like side channels and physical, in fact, attacks on the devices because it's the same hardware, right? It's the same hardware where you're running regular workloads and security critical workloads, and that gives attackers a way to attack these security critical workloads. And in fact, these are two attacks just from yesterday. One of them, in fact, is a physical attack that requires a physical interposer between your CPU and the DRAM chips to be able to compromise the encryption. So these attacks are evolving, and it's the industry needs to in the long term address these attacks, and there's a bunch of interesting research happening on how do we make sure that this hardware is robust to these kinds of attacks. Just one more slide on this new research lab that we are setting up called SPARC, which we're founding. One of our missions is to think about confidential computing at real scale, right? At the scale of what we call AI data centers. So what we imagine is as our North Star is a world where all AI runs by default in confidential computing environments in what we call confidential AI data centers. And this is a world where not only are AI applications and workloads protected using confidential computing, but in fact, all of the cloud's own services and the cloud's trusted control plane, including DNS, certificate authorities, and identity and access management systems are all protected and isolated from attackers using confidential computing. And ideally, all of this on sovereign confidential hardware with strong supply chain guarantees, right? So this is our North Star. And if you're interested in research in this space, please do talk to me offline. All right, so hopefully I've given you a sense for why this technology is important and why I think you might not know it, but a lot of us, in fact, already rely on this technology at real scale. But we still have a ton of work to do. And if you have questions, thanks a lot. And I'll take some questions now.
So much, Kapil. I think we'll take a couple questions. Yeah.
Yeah, so a lot of the trusted execution environments rely on very, very standard crypto, right? So the memory encryption is usually AES. So that's what is used to encrypt. Now, we might not use AS256, we might still be on AS128 for various legacy reasons. So that is standard AES. Attestation is just regular digital public key signing, right? So yeah, it's just basically there is think of these manufacturers essentially creating their own PKI. So there is a Intel root and an AMD root and an ARM root, and this PKI is in the end issuing these keys that live in each device, and these keys are essentially used for signing these attestation reports. So it's just there is no fancy crypto here at all. Yeah.
So one of the challenges, what is safety aspect of this state computing unit? For example, malware uses easy or attacks.
Yes. 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 That's a really good question. So at least the more pragmatic way we think about this is that when we deploy applications in these secure environments, we need to follow higher standards of security to ensure that we are programming in a certain way, and we are trying to make sure that the code is less susceptible to attacks. Now there is no perfect security, and the way we are at least trying to set up infrastructure to deal with these kinds of attacks is this idea of code transparency. So the idea here is that you make sure that every time you build, you do builds in secure environments, and you publish and make the measurements of your code and all of your dependencies, including SBOMs, available to third parties who you want to trust your code. And then you have a way of ensuring that as soon as you detect vulnerabilities in your stack, you are able to quickly recover from those vulnerabilities, publish new versions of your code, and then give a guarantee to your end user that you're always running the latest code, right? Often what happens in systems is that, you might have known vulnerabilities, people don't patch, and then, this malware can stay for a very long time, right? So what confidential computing is forcing hardware manufacturers to do, and also I think as a software ecosystem we need to do better, is to ensure that as soon as vulnerabilities are known, we upgrade, we patch, and we have systems that can force us to enforce those guarantees, right? So that is where this whole idea of code transparency is moving, and it's a whole separate discussion, but happy to chat to you offline.
I think one question here
Yes.
in the front row.
Yeah, I was just curious, what is it that software encryption can do and software-based security compared to hardware? And I was just thinking of cases where sometimes you might trust the cloud provider, but may not trust two customers
Yes.
to talk between.
Yes.
So if you can just say, what is the limit of software-based security, and then
Yes.
what hardware?
Yes, that's a very good question. So, yeah, there are multiple threat models. I didn't go into the threat model here, but confidential computing can serve the threat model where you have a compromised cloud provider. It can also serve a threat model where you have a service provider that you don't trust, but you are an end user of that service, and you don't want to trust the service provider. And that is what confidential containers is trying to do. And the multi-party compute is one instance of that scenario where you have a service that nobody wants to trust, but everyone wants to pool and share data sets, right? Where confidential computing by itself is not useful, or at least doesn't have a direct solution, and you have to combine it with other pets, is things like privacy, right? So if you want end user privacy for data that leaves the confidential computing environment and goes to an attacker, obviously confidential computing doesn't help there, right? And there are other kinds of things like in the machine learning space, all of the kinds of attacks that Nishan described, data poisoning and so on. You can have confidential computing to give you stronger transparency and visibility into the supply chain of your models and data, but confidential computing by itself is not going to solve the data poisoning problem, right? It can give you guardrails, but it doesn't directly solve those problems. Yeah.
Confidential containers we currently tried out in an on-prem solution.
So Kata containers is getting there. We are not there yet. A lot of the confidential containers are proprietary cloud-specific solutions, but Kata containers will help with on-prem deployments because it is a
Hybrid model just like the regular.
no. In fact, you should be able to run Kata containers completely on-prem. No hybrid. You should be able to, or in fact, anywhere you deploy a Kubernetes cluster, Kata container should work. Kata confidential containers. Sorry. So that is a cross-cloud, on-prem, hybrid, all of that.
What's the timeline?
It's in fact deployable today, right? You can deploy it today. It's not a product in the strict sense because it's still under development, but it works. It works on Azure, it works on GCP. You can deploy it, but there isn't like a
Azure GCP, but on-prem.
No. So on Azure, you can deploy Kata confidential containers, not the Azure's own offering, right? And on-prem also, you can deploy it as long as it's a Kubernetes cluster with the right support, with the right hardware, obviously.
Sir, I want to share sensitive personal information in a secure environment, and I want to use memory encryption for that in this CCP platform. So can I use pseudo method? So that because it is going out of my security services and as well as the environment.
Yeah. So the idea with confidential computing is that you want to protect data not just when you are sharing it in transit, but you want to protect it also when it's in use on the other side, right? Where you don't have control. You can always encrypt it. You can also use things like tokens and so on, right? To do encryption at the application level. That is perfectly fine. I think what confidential computing is trying to do is to do it at the platform level. So you don't have to change your workload. You don't have to change how you transfer your data. The platform takes care of you. The platform takes care, obviously, if you use TLS, platform can take care of encrypting data to at least to the gateway or wherever, right? But if you want end-to-end protection, confidential computing can do it at the platform level because all encryption happens in hardware, in an ideal world, right? You don't have to change your application, change your data set. You can actually do data transfers of data that is, that has privacy information, and you can get a remotely verifiable guarantee that it will be processed only by tasks and for a purpose that you are authorizing it.
So I can impose purpose limitation.
Yes. Through attestation, you can impose purpose limitation because as long as you can do this key release in a way that releases keys of your data only to an environment that is running exactly the right code with the right configuration.
I'm going to have to cut this Q&A short in the interest of time, but please feel free to catch up with Kapil during the breaks. I'm sure he'll be happy to take any questions you may have then. But we have to keep the ball rolling. Apologies. A big round of applause for Kapil, please. Thank you.